voice.
I just hope that the stream got that. There was the Game of Thrones intro. Hello and welcome back to Calculus1 for one last time. Yes, we are at the end. The end is near. And this is the part 2 for our U sub. And we need to take care of U substitution for definite integrals. Before we jump there, let's quickly review what the U substitution is about. It's a backwards chain rule. We know that integrals undo derivatives, so a derivative technique, chain rule, has its backwards U substitution for integration. And we talked about, let's say, the problem like this one here. And we said that this problem would be very easy if this was just x 283 rather than this mess 283. So instead of having an x there, we have 3x plus 5. So what we did is we took that 3x plus 5 and we set that up as a single variable. And as soon as we did that, the problem transformed into a basic integral, the polynomial one, right? And we were able to quickly integrate, put plus c, right, for indefinite integrals. And then instead of u, bring back x by using u equals 3x plus 5. So we have the final answer there as 3x plus 5 to the 84 divided by 252 plus c. So now we would like to bring these problems a little further and use definite integrals for the U substitution. Let's put a title. Definite integrals with U sub.
Who advised that we not make our notes at the back of our exam? Will we be needing this paper again?
No.
Okay.
So now what we have is a definite integral, let's say from 1 to 3. And say you have um, 3x square root of 4x squared minus 1 and then dx. So now this is definite integral because we have the numbers.
Oh, yes.
And these numbers are x values limits. What this integral represents is area under this function here, whatever it graphs to. We don't know what it graphs to, so it's some kind of line. And then between 1 and 3, we're looking at the area under the curve. So this line is 3x square root of 4x squared minus 1. Again, you can go on a graphing utility, or you can crank that long calculation, right, that we had, the 13 points stuff. You can do all of that. But we actually don't care what the function looks like. We just say we know what we are looking for, which is the area between 1 and 3. So that's that. So now what we're going to do is we're going to do the U sub for the stuff under the square root like we did yesterday. So u equals 4x squared minus 1, and the du is immediately 8x dx. Do we have 8x dx? No.
Not on the surface.
We have the 3x, right? So we're going to put 8 and 1 over 8 in front. So now our peanut over here, there we go, is a 3 hump peanut. So we have 3 over 8 integral of square root of u du. The 3 that was in front of the x jumps in front of the integral because it's not a part of the peanut. So it becomes 3/8 in front. And then 8x dx is du. And we have a square root of u over there. Yes? Which one?
Oh, I see.
When you differentiate.
That means the 3 can be factored out again.
You'd say x. So you need 8. You don't have 8, so you put 8 and 1 over 8 in front to balance it.
Yeah, okay.
So you can do the substitution. Alright guys, now is the new stuff. This is new. You have done your u sub for the function, and this is what we did yesterday. The new part is to change these limits 1 and 3 into the new limits over here that will correspond to those 1 and 3 but in the u domain. Now u1, which is the lower limit, is going to be 4 times 1 squared minus 1. So you will plug in your x1 in the substitution, which is 1 in this case. You will compute this mess, and we will get 3 as the lower limit. u2 is the upper limit, which is 4 times 3 squared minus 1. Now 3 squared is 9. 9 times 4 is minus 1 is 35. So these are my new limits. Now the cool thing here with these definite integrals is that we do not have to go back to x because we transformed limits to u. So now when I integrate this, which would be, this is u to 1/2, so u to the 3/2 divided by 3/2, we will be computing 3 to 35, and we do not have to convert it back. So now we have 3/8 times 2/3 times u to the 3/2 from 3 to 35. And now we need f of b minus f of a, so upper minus lower. 3's will cancel, these will cancel, so we get 1/4. 35 to 3/2 minus 3 to 3/2. There's no plus c in this case because it's a definite integral. As you can see, there are no variables here, right? All we need to do is to take the calculator and just, if you're interested in decimals, calculate all of this. It's not necessary. You can if you want to, or you can leave it as the exact value. So I'm just going to box this because you can leave it here, or you can go and you can calculate the decimals if you want to. Let's say you have integral from negative pi over 6 to pi over 4 of sine x, let's just do sine x cosine x dx. It's good enough. This problem can be done in 2 ways, depending on how good your trig identities are. But we'll do it the obvious way, and then I'm just gonna, put my boss glasses on and work out the other way as well. So the obvious way is to say that u equals sine x. When I taught this yesterday, I said look for function derivative pairs, because that will give us the clue what is the function, what is going to be the derivative. So now du is cosine x dx. And our integral now becomes, so sine x is going to be u, and cosine x dx is du. So all I need to work on here are the limits. So u1 is sine of negative pi over 6, which would be negative 1/2. That's what we have for sine is odd function, it preserves the negative, and then you just have sine of 30 degrees is a half. And then u2, which is sine of pi over 4, that will be root 2 over 2. So the limits are negative 1/2 and root 2 over 2. So your pi limits are limits for x, and red limits are the limits for u when we do the transformation. So your transformation here is u1 is a function, right, of whatever your u sub is, and you plug in the limits one at a time to transform them into u limits. So now when you have this in u's, we are going to integrate. We get u squared over 2 computed from negative 1/2 root 2 over 2. So this is 1/2 times square root over 2, square root of 2 over 2 squared minus negative 1/2 squared. Now luckily we can compute all of this mess. So 1/2 open parenthesis. When you square root 2, you just kill this, so it's going to be 2/4 minus the negative dies because of the square, so we get minus 1/4, and it's going to be 1/2 times 1/4 is 1/8. What happened?
How did this become a subtraction problem? How did this multiplication?
Are you talking about this?
Yes.
It's f of b minus f of a when you're solving definite integrals.
Of course. I forgot.
So that's the minus, yeah. So here is the entire problem. What I did here is I used u equals sine x, and then we transform the limits when we integrate, so we get 1/8. Now question is, can I get this same answer if I do this same problem just a tad different? Let's see. We have integral from negative pi over 6 to pi over 4 sine x cosine x dx. Now this is the boss way, as I mentioned. Yes. Beautiful. The boss. You should sport the glasses too. So the formula that I am going to use here is that the sine 2x is equal to 2 sine x cosine x. Now I don't have the 2, so I can fix that like this, and the problem collapses into 1/2 negative pi over 6 to pi over 4 of sine 2x dx. Now we just killed the u sub, right? Because you can integrate sine x easily. So we have 1/2 of negative cosine 2x over 2 computed from negative pi over 6 to pi over 4. So now this becomes -1/4 outside, and inside the parenthesis you have cosine 2x computed from -π/6 to π/4. So now we're going to plug in the values. We have -1/4. We have a cosine of π/2. See, cosine of π/2, because 2 times π/4 is π/2. Minus the cosine of, now cosine is even, so it's going to kill this negative. So cosine of π/3. This is equal to -1/4. Cosine of π/2 is 0. Minus cosine of π/3 is 1/2. -1/4 times -1/2 is +1/8, as we have foreseen. So that's the same problem. Now, you know, trig is really cool because we can do all of this mathematical gymnastics to, with the help of all the formulas, to avoid, in some cases, working harder mathematical techniques, right, if the easier ones are option. So in this case, we actually, in this method, did not use U sub at all, because the trig formulas help with this. Good. Anything else? I think, let's do one more problem.
Yes, I'd like to go through the thing.
And, well, actually, let's do a few more, because we can. Plus C is only for indefinite integrals. When you have values, then the plus C actually cancels. Because when you do the antiderivative over here, you would have technically plus C. But then when you substitute here, you would have a plus C, and you would have a minus plus C again. So plus C minus C cancels. So that's why we don't have a plus C for definite integrals, but we definitely have a plus C for indefinite integrals. That's 1 out of 3 for today. That's it. 3. That's it. Well, let's see. Integral from 0. No. From π/6 to π/4 of the cotangent x dx. Try this one. We had the tangent yesterday. It's going to be the same steps. You too.
Going to the tutor. I'll come back to remind you about the grade.
So what is the first step?
You can turn it into cosine x over sine.
Cosine x over sine x, good. And then use the u sub, good.
And then we can see that as d of u over u.
Yeah.
Yeah.
Yep.
Just qualify this because I didn't pick one specific one. I need to pick a specific one. Even though I got it right. I didn't know which one that I would need the help for. I didn't know that was a
That's
thing.
exactly the stipulation of the problem. That's the reason why I have it. We'll talk later. So you said write this as a cosine x over sine x dx. We still have pi over 6 to pi over 4 as limits. Then we have u equals sine x, du equals cosine x dx. Then we get du over u, u1, which is a lower limit, is a cotangent of pi over 6. And that is no, so not cotangent, sine. You're welcome. Sine of pi over 6 is very good. And u2 is the 1/2, right? And sine of pi over 4 is root 2 over 2. So we get ln of u computed from 1/2 to root 2 over 2, which is further equal to ln of root 2 over 2 minus ln of 1/2. Now, are you ready for the boss moves? This is still, okay answer, but we can do better. When you have subtraction of two ln's, you can condense that into a division of arguments. So ln root 2 over 2 divided by 1/2. So that's that rule we reviewed. And then these cancel. So the whole thing is ln root 2. You can actually kick the 1/2 in front. So this is the boss answer right here.
Would it technically be, would it technically be wrong if we didn't replace the limit of du over u with the 1/2 and the 2 value and just use pi over 4 and pi over 6? Because when you replace u with sine x again and you evaluate it, you get the same answer, right? So
yes.
Do we have to, or is it just good habit?
It's a good habit because I've seen way too many times where students say, let me not worry about limits. I will get to it at the end of the problem. Then someone sneezes, you lose that piece immediately, and then at the end of the problem you put plus c and you move on without computing the limits. So I've seen that way too many times. So I don't even put it down as an option. I just say convert the limits every time, because these procedures get more complicated as you go to Calc 2, Calc 3. And having this as a quick response. And it also teaches you that, x limits go with x variables and u limits go with u variables. So that's another thing that's going to be very useful in Calculus 3 eventually. So I don't like to play the game. Now, can you do what you suggested? 100% of the time. But as I said, not everyone has the same focus. And I've seen many times students forget to go back and plug the limits. So probably you notice that I am a stickler for notation. Some of you also seen on your exam, right, when you write, limit equals 5, and I say, no, -1 notation, because limit doesn't equal 5. LIM means nothing, right? You have to have function plugged in, you have to have something under the limit. So, because it's universal language, right? You can communicate through these equations with any other human on the planet, regardless whether you know their language or not. If the notation is correct, notation is the same everywhere. And that's the clear benefit of this. This is the only, truly universal language on the whole planet, because it's the same notation and the same rules everywhere, because those are the only rules we can actually have. What else should we?
But I suggest we do some practice with rhyming stuff.
We'll do that in the review. We're still working on 5.5. So let's do another example. So 1 to 7, let's say, of root x plus 9 divided by 4 root x dx.
Hopefully you didn't say Right. Okay.
Did you ask your website? Ask your website? Oh, good.
We'll trade you his information on the website if you tell us the answer.
So I know the answer.
Oh, no, you don't. We don't. You do that?
Everyone is actually very quickly. Yeah, it can be also helpful. It just depends on what type of problem you have, right? You saw the derivative, right? The logarithmic differentiation goes like this, no matter how complicated it is. So if there is a trick to do it, you can do it. If there is no trick, right, then there is the finite computational power, then yeah, it's gonna be an issue. So. I thought it was something else. This.
Same thing. And then you plug into have
So what's u?
or like that. No, I mean x squared plus 9.
Root x plus 9, yes. And a du is 1 over 2 root x dx. So now what I'm going to do is I'm going to break this 4 into a 2 and a 1/2 in front, right? That's the elegant way to do it. So now we have 1/2 integral, and this is just u du. And now I have to change my limits. So u 1. Oh, who picked 1 and 7? We're gonna go from 1 to 9. It's very easy to change a 7 into a 9. So change your 7s into 9s. Those are terrible limits. So u1, we plug in 1, so we have a square root of 1 plus 9, which is 10. So the lower limit is 10. And the u2 is the square root of 9 plus 9, which is 12. Much better. So now when we integrate, we get u squared over 2 from 10 to 12. That's 1/4 of 12 squared minus 10 squared, which clearly is 11. Good. So this is the u substitution.
Yes.
And this is the great time for us to go into this 10-minute talk for Calc 2 prep. And then I have 5 to 10 minutes talk. If you are not taking Calc 2 or don't care, you can just leave. But here it is at the end. So Calc 2 prep. So many of you heard the stories of hell on earth, the hellfires and everything else. And that is true only if you go to that class unprepared. If you are prepared well for that class, you have no issues. So what are the concepts and sections that you absolutely need to know to survive Calc 2? Well, first of all, half of the Calculus 2 is integration, and the other half is limits, okay? So the entire course is driven by like 5 sections from Calc 1. And if you don't know those 5 sections, you are going to have trouble. And then there are also some trigonometric identities that you must know, and you will be perfect in that class. So to start off, the first half of Calculus 2 is integration. So you absolutely must know these 3 sections. So integrals, to prep yourself. 4.9, which is where you learn all of the basic formulas that you have for integration. Followed by 5.2, which contains your definite integrals. And then the grand finale here in blood, 5.5. Most of your integrals in Calculus 2 will be used substitution integrals. Because, let's face it, most of your derivatives were chain rule, right? Well, that makes sense to have most of the integrals to be the backwards chain rule, which is a U sub. So that's for integration. And then for limits, which is the base of calculations for the second half of your calculus for sequences, series, and power series, the limits, you will need limits at infinity, and I believe that was 2.5.
Okay.
Limits at infinity, and then you will need L'Hopital's rule, which is 4.7.
See,
2.5.
2.5.
So limits at infinity, that's when you have limit of x goes to infinity, because all of your limits will be going to infinity in this, all of them. So 2.5 and then 4.7 to calculate, because many of these limits will end up being L'Hopital rule. So these are the 5 sections, and technically, if you don't know 5.5 and 2.5, just do yourself a favor and don't sign up for the class, right? So that's one. Now, for trig identities, this is another pile of stuff you need.
4.7.
So trig identities,
That's the L'Hopital's rule, right?
yes. So trig identities you must know. And these are that the tangent theta is sine theta over cosine theta, that the secant theta is 1 over cosine theta, cosecant theta is 1 over sine theta. So those must be known.
Is that it, or you kind of all of it together?
I'm going to list all that you must know. Now, the more you know, better off you are, because here and there, the other one. See, if anything that I don't put on this list, it sneaks in, it kills 1 out of 1,000 problems you're going to do. So everyone makes mistakes, right? I remember the problem I missed, so it's okay. But no. Calc 2 was my B+, okay? So yeah, it was hell on earth. I was not ready for that class at all. So we have tangent theta, secant theta, and now we need Pythagorean identities. We have 3 of those. Sine squared theta plus cosine squared theta equals to 1. That one is a must. And now the 2 companions Now, the two companions are very easy to obtain. If you divide the entire equation by sine squared, you get one, and then if you divide the entire equation by cosine, you get the other one. So those are 1 plus tangent. So if you are dividing by sine, 1 plus cotangent squared theta is equal to cosecant squared theta. And if you're dividing by cosine squared, you get tangent squared theta plus 1 is equal to secant squared theta. Note that these formulas also preserve that sines go with cosines, secants with tangents, and cosecants with cotangents, right? You see that the pairing is preserved in these formulas. You will be using this in two integration technique sections. One of them is trigonometric substitution, and the other one is trigonometric integrals. So you will need these formulas. And finally, in blood, well, no, I have 4 formulas to go, but in blood, power reducing formulas. These are extremely important. Sine squared theta is 1 minus cosine 2 theta over 2, and cosine squared theta is 1 plus cosine 2 theta over 2. There is no other way to integrate sine square or cosine square other than these two formulas. So if you don't know these two formulas, you just can't get anywhere with the problem. U sub doesn't work. It's not a basic integral. None of the techniques you learn in Calc 2 work. The only method to integrate sine squared is to use this formula. And finally, the double angle formulas that we used earlier. Sine 2 theta is 2 sine theta cosine theta, and cosine 2 theta is cosine squared theta minus sine squared theta. And this is your list for Calc 2 prep. If you are taking Calculus 2 in 2 weeks, right? Because the class starts in literally 12 days from today. If you are taking Calc 2 in 2 weeks, about 2 weeks, this is the list that you need to know. And Calculus 2 is not going to be an issue. Now, you guys already had Calc 1. Your U sub should be fresh 10 days after you took the final. Otherwise, why you're bothering with any of this stuff, right? This is definitely not for you if you're going to forget U sub, right, 2 weeks later. It is a very important and very much used technique for integrals. So you really need to know it. I do review, obviously, all of these formulas as we go on, but Calculus 2 is very heavy on prerequisites. And that's why, right, usually what happens is students come from classes where U sub is rushed. I always make sure I have 2 classes on U sub because you're just dead in water. Your first exam in Calc 2, your first exam is all of your integrals are either basic or U sub. Integration techniques are studied on the second exam, right? The first exam, which is chapter 6. Chapter 6 only has basic integrals and U sub integrals. And if you don't know 4, 9, and 5, 5, well, your score on that exam is 0. Because the only thing that you are learning for the first test in Calc 2 is, I would say, 10 formulas. You have to memorize 10 integral formulas. You have to memorize 10 formulas. You are not learning new methods of integration. The only methods of integration you have is the U sub or a basic integral. So something like this, you will plug in the derivative, you will, right? You will compute.
This is formula from Calc.
That's from Calc 2, yeah. So don't have to write it down. So
Photograph.
if you don't know right? If you don't know, it's in the book. If you don't know U sub, you can't solve the problem. That's the deal. So your first exam in Calc 2 has, I don't know, 70% U sub, 30% basic integrals, 100% integration. You will probably take 2 or 3 derivatives on that test as well. That's your Calc 1, that's your Calc 2 exam 1. It's exam 2 where you learn integration by parts, trigonometric substitution, trig integral by parts, partial fraction decomposition and all of these other things. That's chapter 7, that's exam 2. So it's a really balanced course in terms of exam 1, 2, and 3, so it's not a big deal. Balancing in Calc 1 is not that great. We had 6 sections on the first exam, right? Plus pre-calculus review. And then your exam 2 on chapter 3, 11 sections. So how's 11 section compared to 6? Right? It's almost double, right? Calculus 2 is very well balanced, 10, 10, 10. Right? It's really good. Well, one of them has 9. I'm not sure which one, but it's very well balanced. So it is not crazy course. It's not crazy course because it's crazy. It's crazy because of the prereqs. And if you tend to forget the prerequisites, if you don't know these calculus, these trig identities here, you are going to have a lot of trouble in that course. And clearly, relearning Calc 1 and relearning these identities from trig while you are memorizing all of the Calc 2 new stuff, well, you are learning 2 or 3 courses at the same time. Of course, it's going to be hell on earth. Which is why I always suggest to students, prior to Calc 2, if you are taking it now in the second half, you guys have 12 days, right? Work these formulas out. Write them 50 times on the piece of paper. Maybe you can find trig identity problems on YouTube. Just a little bit on the brush up, right? Brush up. So when it comes up, not if, but when it comes up in a class, you just go, okay, right? And you move on. Rather than not knowing what the hell is going on in the whole class, sit here like a bump on a lot, then go home and waste another 3 hours trying to figure it out on your own, right? That's a problem. So you have the 5 Calc 1 sections, which are indefinite integral, definite integral, and U sub, and then you have 2 sections from limits at infinity, which is limit with x goes to infinity, and then the L'Hopital's rule. There you go. So those are the 5 sections. I listed integration first because your exams 1 and 2 will be integration, and then limits in a second. Well, there will be one section on limits in integration, but that's one section. So you will use both of these sections in that section in chapter 7. But every single problem of chapters 8 and 9 will be limits. So you want to know limits for that. And that's it. Now Calc 2 will be heavily used in differential equations. So what you learn in Calc 2, so this is why I say, if you have very poor knowledge going into Calc 2, chances are you're not going to make it in Calc 2, and then if you somehow by some miracle make it to Calc 2, then differential equations becomes, because it compounds. In order for you to do Laplace transform, you have to know integration by parts. Integration by parts is U sub on steroids. So, right, inverse Laplace transform, partial fraction decomposition, which is ln integrals. The U sub with the ln we had in class, where you have the denominator and then the derivative on top, all of those. So that's the prep, and take a short break. When we come back, we'll do some review for any questions you have as a review for the final. Bye.